All right, so we'll get going today with doing some more work with chapter 2 of the textbook, doing some exploratory data analysis and just really getting us comfortable with R. So just want you guys to know, that first exam covered some probability or total probability, which we'll be using throughout the semester. But we're gonna kind of change gears a little bit when we're doing some statistics. So I kind of just like quickly looked through some of your work on the exam. And so things like evaluating integrals seems a little bit rusty. The calculus seemed a little bit rusty. That's not generally a good thing, but it won't. I just want you to know that like we'll be using a lot of stuff in R right now where it will be less calculus focused, but that stuff will come back. So I just don't want us to totally ignore that. But I think right now, if you get really hunkered down in R and start to get really comfortable with R and not kind of skip any steps along the way, regardless of how the first exam went, you're pretty much starting with a clean slate, and you can go right into the next exam and do really well, even if you didn't do as well as you wanted on the first exam. But I don't know how the first exam went. I'll get through grading that over the weekend, and I'll let you guys know once those are done. So for next week, the plan is going to be back on kind of normal schedule with quizzes on Monday and Wednesday. And a homework assignment is not going to be due until the following Monday. So I will get that assignment up. It won't be due next week. It will be a little bit longer because it's going to contain more than just a week's worth of material. So I would definitely encourage you guys to get started on that. Well, once I get it up, you need to know the questions first to get started on that sooner rather than later. But any questions before we get started for today? Okay, so I am going to try and stay on my iPad, although we're going to be doing stuff in R. I tried to just like paste the code into this document since I realized watching the recording of me using the, sharing my entire screen made R a little bit small. So I'm just going to try and keep things organized over here. I would encourage you to have a window RStudio open and try these commands out on your own and make sure that they're working for you. So last time we were working mainly with categorical variables. So these are things that place our observations into categories, like were you a United flight or were you an American flight? And then we looked at bar plots and compared some proportions to, for example, take a look at which carrier was more likely to have a delayed flight. Today, or at least here, I want to kind of change gears and think about how we could present numerical data. So the variable that I want to take a look at is going to be what's called flight length. So this is telling us how long was the flight in minutes. So this is a numerical variable. And so when we're displaying numerical variables, we typically use a histogram is one way that we typically present numerical data. So it is a bar plot where we first place all of the observations into what we call bins. Let's kind of talk about how we could create and read a histogram for this data. So over here, I've got two different ways that we can filter or subset the data. And so if you remember kind of what the data looks like, right, we have a table in the background. We've got all of these flights, and one of the variables is carrier. And again, there's two possibilities there, American or United, and another one is flight length. And that's telling you the minutes for how long the data set is. So I could certainly plot all of the data together, but let's say I wanted to get like an idea of how did the flight length distribution for American compare to United. Then what I need to do is kind of take this data set and essentially split it into two separate data sets. One that only contains all of the American airline observations, and one that contains just the United observations, and then we can plot those separately. So this is what's called subsetting, filtering the data. So one way to do it, I'll kind of say, well, we'll kind of use it this way today, would be to use the subset function. We're going to use this quite a bit when we're writing our code to do more complicated statistical tests for us. So just to be clear, what is going on in this code is first, this is saying enter the data set that we're working with. So that's the data set called flight delays. This is telling it to which variable or variables, you can enter more than one, do you want to pull out of this data set? So that means it's just going to create a data set that has just one column of data corresponding to the flight length. And this last part over here is telling us which observations are you picking out of the data set flight delays. So just to kind of back up, it's going to say, go into flight delays, pick out only the observations that have American as the carrier, and select only the variable flight length over here. And so before you run this command, just be sure that you need to load the data set, which sits inside of this package resample data. So if you do library resample data, and then you enter this command below, you probably won't see anything in the output because you're taking this output and assigning it to this new data set that we're calling AA. So any questions on how that subset command is working in R? Okay. So yeah, I would definitely kind of encourage you guys to check it out. And if you really want to see what it looks like, then I would suggest also loading the data set tidyverse. And after you do that, the view command will work. You can do view AA just to make sure it looks like what you think it would look like. And then you could actually see the output. Okay. Any questions? Is that working okay for you guys? Okay. I'll take that as a yes. Cool. So like with most programming languages, there are like multiple ways that you can do things. So I just want you to know that like another function which does a very similar thing is what's called a filter. And for anybody that has programming experience in other languages or with R, I just want to kind of introduce some other stuff. So if you're comfortable with the subset function, you don't need to learn how to use this. You can just pick one way of doing things. But this little symbol over here is what's called a pipe in programming languages. So anyone that's programmed in other things, you probably have a pipe. Sometimes they're in other languages, it might be a vertical bar or some other things. And so what this is, it's like composing two functions in some sense. So it's saying input flight delays into this function filter. So it's going to say filter this data set flight delays and pull off only the observations that have AA in it. So it's almost like a function. It's saying like input this into this command over here. And it works the same as doing so it would work the same if I did it all in one command. So you don't have to use the pipe, but pipes are nice if you're used to them in other languages. And the difference between these two, if you view this data set, AA1, the difference here is that it didn't just pull off flight length, it pulls off every variable. So it's just really going to take the data set flight delays and create a data set AA that has all of the information that we had in the original data set, but just the American Airlines flights. Okay, I can imagine everyone in the black screens is going like this. That makes me feel better thinking that. Okay. Thank you, Karina. Cool. Okay, you guys are fine. I'm not meaning to make you feel bad for having for not being able to turn your cameras on. Okay. So if I want to create just the American Airlines histogram, kind of step one is subset the data. So now I've got a data set that looks like this. And then I want to create a histogram of that information. So that I can do with this command over here. And so if you're entering this in the console, like in the lower part, then I wouldn't hit enter, right? Because enter is what executes the commands. You can just enter this all on one long line. If you're using the script, then you can hit enter because it won't execute the script until you run it. But histogram is the code, and so it works similar to bar plot in that we say, take the data set AA, which is the one that I created just up here, and then create a histogram from the flight length variable in the data set AA. This is telling it how many bins to set up. So that means we've got 1, 2, 3, 4, 5, 6. Here's a 7, an 8, a 9. Oh, did it do an extra one? That's weird. I see. So this is saying 10 and 11. So this is interesting. Actually, 10 breaks gives us 11 bins since it's counting the breaks. So it's like 1, 2, and so on. The X limits tell us go from 140 to 250 on the horizontal axis. The Y limits say go from 0 up to 650 on the vertical axis. And then you can pick your color. I'm going to claim steel blue. That's mine. You guys can't use steel blue. Feel free to choose your own color. I'm just kidding. You can use steel blue. It's a fine looking color, I would say. Or you can choose nothing and it'll do a default, which is probably black or gray. Okay, and so as far as the histograms go, what it's doing is how you would read this is we would say there's about 500 flights, American airline flights that were between 140 and 150 minutes long. So down here, we actually read the value of the variable, which would be minutes of the flight. And up here, we're reading the frequency or the count of how many things are in each of these bins. So this is not a distribution in that sense that the vertical axis is telling us how many things are in each of these bins. Okay, any questions? So what I would suggest be a good idea is why don't you guys try doing the similar thing but with United flights. So we want to create a histogram for United. So I'll say kind of step one would be to subset or filter out the UA observations then create this histogram of UA flight lengths. So as far as like the subsetting goes, what would I need to change about this line of code that we did for American? You guys can chat if you're kind of hesitant to talk today.
We changed A to UA.
Yep. So rather than put an A here, we could put a UA. It does need to go in quotes. That's important. We can change this, right, to something else. Probably UA would make sense. And then we could run the histogram code, just changing that as well. And if you want to check to make sure you're getting the same thing that I got, it looks quite different. This would be the distribution, the histogram for the flight lengths for the American flights. Okay, so this is the part that's scary. When I'm in a classroom, I can always just walk around and make sure it's working for people. So I'll trust it for you guys to let me know if you're having trouble. Please don't hesitate if you're like, this didn't work for me. Probably somebody else made the same mistake. So this is the point of us being together right now, is so that you can get some in-time feedback as if things aren't working. Is it working, not working? Okay. Good. So when you're handing in your work, I think that you might find things a little bit easier to type up in some sense when we're using R as opposed to handwrite it, since you're going to be typing it into the R console anyway. So that's something to think about. But when you create some graphics for this next homework assignment, I'm going to ask you for the code and for the output of that code. So if this was a homework question, then I would want to see, this command. I would want to see the fact that you needed to load the resample data library. And then I'd want to see like the histogram code that you went. So you would need all three of those lines of code in order to create this histogram. And then I would want to see this image over here. So once it's created in that little box in R, there's an option to like copy to the clipboard and then paste it to whatever document you're working with. But if you're having any problems figuring out how to organize your work, just let me know. Any other questions about the histograms? So not only creating them, but also be sure that it makes sense what you're looking at, how to read them. Okay, so here's worksheet 8B, kind of just picks up where the last one left off. So we're still talking about exploratory data analysis. We're working in chapter 2. So we looked at we looked at United distributions separately. If we want to compare like which of these two flights, which of these two airlines operates flights that generally are longer than the other, we don't compare proportions like we did with categorical data, but with categorical data, we compare proportions. Was the proportion of United flights that were delayed more than the proportion of American flights? With numerical data, we compare centers of data, and that might be the mean, that might be the median. And it probably helps to compare both of those statistics. So rather than think about what proportion of flights were delayed or on time, here we can think about like what was the average flight length for American compared to the average flight length for United. So what do you think the command in art is for mean? Or take a guess.
Mean.
There you go. Good guess. So R works, it's supposed to work intuitively. So the command for mean is mean. The command for median is median. And what goes inside of the command would be the variable or a vector of values that you would like it to work with. So this, again, is telling us, pull off this was this data set, American Airlines, that we created, right, which only had the American airline observations. So if you calculate these, I didn't put the outputs here. Why don't you guys tell me? You can chat in. So I will set it up. You can just chat it to me privately if you like. That's all you can do at the moment. But I just want to make sure, not quizzing you, I just want to make sure that things are working for all of you.
Do we type the pound mean too, or the number sign mean?
No. So
okay. That's just
yeah.
extraneous. It's just labeling it.
Yeah, so we use the pound sign to add comments. So that means like once you put a pound sign, R will ignore whatever comes after that. So sometimes that's nice. You want to leave comments for yourself, but you don't want R to try and execute those comments.
Okay.
Great, thanks for these coming in. Oh, what did I say here? I said to do it for United, right? But then I have American in my code. So I think you guys are actually doing the American one, which is fine. That's what I have here. So I would say, yeah, do it for that, and then also kind of do a check for that. Great, thanks for all of these coming in. Yeah, so if you're getting an error like the object AA is not found, remember that this was what we created with the subset function. So if you called it something, maybe you called it AA1, or if you called it something different, then you just would want to adjust that over here. Yeah. Great. This is good to see. So yeah, so for the United, you guys can feel free to let me know if you're getting something different. This was about 181. For the median was 160. I actually didn't do American, so I'm going to go off of what you guys have. So I'm seeing responses that this was 175 and it was like 187. Does that look right? I think that's pretty much the consensus what I'm seeing here. Okay. So if we're kind of comparing these two these statistics, then at this point we could say that American Airlines are overall have longer flights than United, right? Doesn't mean every single American flight is longer than every single United, but on average, American Airlines are lasting longer. But we can see here the mean and the median, right? They're telling us different things. One is the average and one is the midpoint. So we could say for American Airlines, or excuse me, United Airlines, we would say the mean I don't want to say means. So what this tells us right, the median divides the data in half. So this would tell us half of the flights were less than 160 minutes, half of the flights were longer than 160 minutes. So why do you think when we're comparing these two that the mean for United is much bigger than the median for United?
There's more variance in the data set?
So it could be due to the variance. That could be a possibility. But even if the variance was big or small, this still might be, we still could get something like this. So the variance is right, that's telling us something about the spread of values. But for example, we could have like everything here and everything over here, the mean and the median, they would be equal to each other, like somewhere in the middle. There's something else going on when we have a much larger average than we do median. Right, so the median's dividing things in half. And for us, we see that the mean is over here in this example. It's bigger than the median.
So there's more data on the higher end?
That's right. So when you see something like the median is less than the mean, this tells us that we have more values on the right. As we would say, there are outliers that are big in that sense, right? There were probably a few flights that were really, really long, and that's why it's skewing the average over the median. So R does these calculations for us. That's great. You need to make sense out of what does it mean when my mean and my median are not equal to each other. So that could be something that you're asked to explain, like, why do you think this would happen in the data? And so these are mean and median are two measurements of center. Okay, and I'll just say the mean is sensitive to outliers. So sometimes you want to put a lot of emphasis on the outliers, and then it makes sense to compare means. This, however, the median is not affected by outliers. So when you're looking at like income distribution in countries, they almost always, well, they should compare medians and not mean income, because the mean income is not very illustrative of how income is distributed in a country, because we've got Bill Gates and LeBron James and people that make ridiculous amounts of money that make it look like the average income is huge, when, you know, all of that income is being earned by, you know, on the big side of things. So when you compare the median, that's a little bit more representative, because it tells us like half of the people in this country make less than this much money. And it makes sense to compare that to some other country or some other state if you're comparing things. Okay, so kind of a good thing to think about describing to me or somebody else would be like, why would you want to compare medians in data sets? Why would you want to compare means? What's the difference? That's really important. So any questions about those ideas? Okay, so those are our main measurements of center. So next, let's talk about measurements for spread. And we've seen the standard deviation, so we'll get to that in a second. But the easiest one to do would be the range. So this is just taking what is the biggest value minus the smallest value. So kind of the pro here is that it's super easy to calculate. The con is that it only considers two values. So this really doesn't tell us anything about how things are distributed between the biggest and the smallest value. We just know what the biggest and the smallest is. So a data set that looks like this versus a data set that looks like this, right? They would have the same range, but things are distributed differently in these two distributions. So that's where the standard deviation comes in. The standard deviation takes into account every value in your data set. And so what you can think about is, so we've been doing this up to this point by kind of calculating the variance and then taking the square root of that. So kind of the first step would be I calculate the mean of my data set. Then for each value in our data set, we calculate the distance of that point to the center, to the mean of the values. So this is thinking about the distance. And so we really want to think about what is the average distance of a point from the center. And so in that sense, we don't want negative distance to cancel out positive distance. We want to think about those distances as positive things. So we do it in a weird way. We square it. And then take the square root of it. So that kind of undoes the squaring process. So the reason why we squared it is we want to treat distances as being positive things, and then we want to undo it. So This part over here is thinking about where we're calculating the average of all of those. And the reason why we use n-1 is because this x bar really depends on all of the x's, so we kind of lose 1 degree of freedom there. But I wouldn't worry too much about the n-1. I wouldn't worry too much about calculating this by hand, because we have this nice handy function in R that will do it for us. But what I would like you guys to consider is, like, what is the standard deviation actually telling me about the data set? So the standard deviation is the most common measurement of spread for data. And it's kind of listed, and I've been using it, but when we're working with samples, like a sample of flights, we use a different set of notation than we've seen when we've been using population data for random variables. So for population, we tend to use Greek letters, and for samples, we tend to use Latin letters. So I think for the reading quiz on Monday, amongst other things, definitely going to make sure that we're comfortable with the notation. So just refer to this part of today. You know, it'll be real simple. Like, here are 4 things of notation. Match the notation to the appropriate statistic. So we call things that summarize a sample statistics. We call things that summarize a population parameters. So that's also important to keep that terminology straight. Okay, how's everybody doing? Kind of quiet. That's either good or bad. Thank you. Okay. Yeah, and so let me just say, with population standard deviation, rather than use the sample mean, we would use the population mean. So that's one change. And with population, we divide by n. Whereas with standard deviation, we do a similar thing. I forgot my sums in here. So we would sum up all of those things, and then for the sample, we divide by n-1. So what's important is, in R, it only does the sample standard deviation. It does not calculate standard deviation for a population. Usually populations are theoretical. We have formulas for them, and we can calculate those, or we know what they are because we know the theoretical distribution. So most of the time when we're working with R, we're uploading a data set that contains some sample of data. So that's why R really is, for the most part, assuming that your data sets are from a sample. Okay, so another way to describe the spread of data is what's called the interquartile range, which is abbreviated often with IQR. And in order to calculate the interquartile range, we have to calculate two quartiles, what's called the first quartile and the third quartile. So the first quartile is just the 25th percentile. So sort of like the mean being the 50th percentile, Q1 tells us that 1/4 of the values are less than it, 3/4 of the values are bigger than it. So in other words, you can think of the interquartile range as telling us the range of the middle 50% of the values. And so we have a 5-number summary for a data set, which tells us these 5 things. What is the minimum value, the first quartile, the median value, the third quartile, and the maximum value. So just to kind of see what this might look like, just to take like a smaller data set by hand, if we wanted to figure out the 5-number summary for this, right, we would identify the minimum, the maximum value. Then we can say, okay, there's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values here. So which value is the median value here?
Should be 20, right?
Yep, I think so. This splits it into 5 values over here and 5 values over here. So we could plop that down over there. So that's what we mean by the divided in half. We don't pick 25, we don't pick the midpoint between the max and the min, but we pick the middle value. And then we would say, okay, over here, we've got 1, 2, 3, 4, 5 values. So that means, right, you can think of the first quartile as the value that splits the lower 50% in half again. So it's like the median of the lower 50%. And this would be Q3 over here. So basically what it does is it splits the data set into 1, 2, 3, 4 equal parts. 25% of the values are here, 25% of the values are here, 25% of the values are here, 25% of the values are here. So the 5-number summary gives us some idea of how things are distributed. This tells me that there's a lot of small numbers because the minimum and the first quartile are really close to each other. So there must be a lot of 1s and 2s I could see from that, for example. Any questions? Okay, so coming back to R, there are all sorts of functions in R to do this. So you could use a first quartile function. So these are what are called quantile functions. The easiest way to do it is just do summary. This is going to tell me a whole bunch of statistics. So if I run that command, you could try it out. So here I'm just doing, I don't know why I keep saying United, but I'm doing American. We'll change that to American. United flights are grounded for the most part these days. They explode over Broomfield. So we'll stick with American for this one. And yes, since it was asked, like this stuff over here, you don't need, that's just me putting a comment like this is what this command is doing. Just to try and explain what's going to happen. So when you're looking at the output here, hopefully you're getting something similar. This tells me that 140 minutes was the shortest American airline flight in this data set. And now I've got my first quantile, my median, be careful. That tells me the mean, which is not included in my 5-number summary. So I would skip over that one. And go to the third quartile and then the maximum. Okay, any questions? Okay, so another way, so when we're dealing with numerical data, kind of the main ways that we can display numerical data are using histogram, which we saw with the hist function. And box plots are the way that we graph 5-number summaries. Right. So sort of drawn to scale. So you should have like an axis drawn to scale on the bottom. And so how a box plot works is we're going to put a little vertical bar. The width or the height of the vertical bar doesn't tell us any information. So it doesn't matter how big that you draw it, but for each of these 5 numbers, we put a bar there. So here's a bar at 1, here's a bar at 2, here's a bar at 20, at 42, and at 50. And then we make a box that goes from Q1 up to Q2 with a line for the median in the middle. And then we draw what are sometimes called whiskers out to the minimum value. And again, what's kind of significant about box plots in general is that it tells us how data is distributed basically in chunks of 25% of the data. So it tells me between the first arm and the start of the box, that's 25% of the data. The left part of the box is 25, the right part is the next 25, and then the part above the box is the final 25%. Any questions? So again, we're typically gonna be working with larger data sets, so we wouldn't necessarily want to do this by hand. So the command is fairly similar to the histogram. It's just a box plot command here. So just so you know, like these little symbols here, you don't type. These just come here just to indicate that I type spaces in the title. So I would definitely encourage you to try that command and make sure that you're getting something like this. Sometimes box plots are drawn this way, sometimes they're drawn that way. So hopefully it doesn't, you could tilt your head and get either way. And that's what this command over here does. The default is to do it horizontally like I did it. Just for space reasons, I wanted to make this one vertical. So making horizontal true would just put it that way. Any questions? Okay, so I would say, why don't you give this a chance just to practice and try and create box plot for United flight lengths. And that one might look really scrunched if you do it vertically. So when I created this one, I changed it to true, so this one was a little bit easier to see. Does anyone know why we have these circles over here and over here?
Those are the outliers, right?
Yeah, so dots are referred to outliers. So if you're curious, excuse me, like what makes something an outlier, we have a more formal way of classifying that. So I'll just hold off on that for now. But the one that I set up, we didn't have any dots, so I was assuming that none of those values were outliers. So sometimes you might not see any dots. I don't think we did on the American one, actually. Yeah, so this one didn't have any outliers, whereas the other one did. So it's interesting, right? We can see things are distributed very, very differently. Like almost all of the United flights were like 160 minutes long. And then they had some that were really long, and then they had a few that were really short. Whereas American airline flights seem to be a little bit more uniformly distributed. We have some that are long, we have some that are shorter. So when we're comparing like two sets of numerical data, like one obvious question that you might think about if we were given this data set would be like, hey, data scientist, tell me like which airline, can you compare like the flight lengths of these two airlines? I work in flight control at DIA. And so that's where comparing side-by-side histograms, or excuse me, side-by-side box plots are often how we could compare two data sets next to each other. And so if you wanted to create that, you can use the same box plot command. We just enter two different variables into that.
So from these two tables, we can pretty much deduce that United is more unpredictable in their flight lengths.
Yeah, well, I mean, also it's, all of these, I guess it wasn't clear like in the data set that these were flights out of Boston, I think. I can't remember what it was. They were flights that left one airport. It was either Boston or Chicago. I think it was Boston. Um, and their destinations were different. So it seems like that here, like there are a lot of really short United flights that were being operated. So these were probably flights going from Boston to other cities on the East Coast. And they probably had some flights over here that seemed to be operating a bunch of flights that were going out to California or the West Coast. Whereas these over here seems like American like was serving the Midwest, right? And if you think about it, well, I don't know how much you know about airlines in the US, but American has a hub in Chicago. So probably a lot of these flights were going from Boston to Chicago and then connecting to go to someplace else. But in any case, that's right. These box plots tell a story, or at least they tell us what questions to investigate to get to the bottom of the story.
So that like spread that we see isn't from a like behavioral viewpoint. It's pretty much an operational effect.
Yeah, that's right. And there
Okay.
could be some of it could be, yeah, I don't know, like, delayed, like when you arrive at your destination, but you kind of circle around because you're waiting for the tarmac to clear and things like this. That could be a part of it too. Yeah.
Okay.
But yeah, most likely, I think these are reflections of where the flights go. And that would be something I would encourage you guys, if you're curious, take that flight delayed data set and say like, you can create a table and say like what were the destinations for American compared to the destinations for United, and that might fill in some of that story. Okay, so I don't want to get into this too much because I'm not going to ask you guys to create these things by hand. But if you're curious about like what makes something an outlier or not, the way that we classify them is we calculate what are called sometimes the upper and lower fences. So basically what this is telling me is that anything that is more than 1.5 times the interquartile range above the third quartile, that's large enough that I'm going to consider that an outlier. And anything over here, which is 1.5 times the interquartile range below the first quartile, that's going to be the lower fence. So just to see how this worked, let me get the 5-number summary for United. So for example, for the United flights, the 5-number summary is 68, 153, 160, 168, and 295. And so this one had some outliers. And so in this case, the upper fence here would be the third quartile, which is 168 plus 1.5 times the interquartile range. And so the interquartile range is the distance, from the third to the first quartile. So by my calculation, that comes out to 190.5. And that's kind of where this arm is going over here. It's kind of going at the value closest to the upper fence, but that is not greater than it. And all of these values over here are outliers because they're above that 190. So that's how those arms and those dots are figured out. Okay, any questions? Okay, so we've got kind of the main ideas today so far have been working with numeric data, how we display it, histograms, box plots, how we summarize it, mean, median, 5-number summary, standard deviation, all of that stuff. Okay, so kind of the last thing I want to talk about today are what are called quantile-quantile plots. So yeah, to do that, we need to think about what quantiles are. But let me just first tell you, like, the point of a quantile-quantile plot is you have a set of data. You might want to think about what theoretical distribution in particular, you're asking, would a normal distribution be a good fit for my data? And that's where a quantile plot would come in, though we can compare it with other distributions, not just normal distributions. So a quantile is the same thing as like a percentile. Just we're describing things in terms of proportions as opposed to percents. So in other words, we're describing them as decimals. So rather than say 95 percentile, we would say the 0.95 quantile. And again, the function for this, if you want to find something other than the first or the third quartile, you want to find some other quantile, then you just enter the data name, and over here you enter what probability you're looking for, what quantile you're looking for. So if you were looking for like the 90th percentile, you would just enter 0.9 for P. So just be sure you're doing proportions and not percentages. Okay, so let me kind of bounce over 10 for a second. So let's say I have a data set of 10 exam scores. These are not your exam scores, just random set of exam scores. And I want to ask, you know, what were the scores on this exam normally distributed? Or did the class follow some other distribution? So the way we could set up a quantile plot be, okay, take my 10 values. And so my very first value, 55, it is going to be, I'm going to associate that as being the 1 over 11 quantile. The 11 coming from n plus 1. And then my second value, I'm going to map that to 2 over 11 and so on. Again, these plots are created by R. We need to make sense out of them. And so sometimes I think it is useful just to see how they're created in order to make some sense out of what we're looking at. But then luckily for really large data sets, we don't have to do this by hand. So this is kind of telling me the quantiles and I'm going to compare my quantiles to what the quantiles are for a normal distribution. So what Q of 1 over 11 is for the very first one it's going to tell me what is the value of the z-score, really, so that the area to the left of it is 1 out of 11. Right, so I'm going to try and find the equivalent of the 1 over 11 quantile for my data set is 55. What was it for standard normal distribution? So what's a function that I could use to help me find out what that value is? So I can't use this function up here because I don't have a data set, right? We're working with the standard normal distribution. So this is a theoretical data set. But luckily, right, R has built-in functions to deal with theoretical data sets. So what was the function for normal distributions that found quantiles?
Was that Q norm?
That's right. Yep, it was Q norm. So that's kind of the theme of R is, right, if you've got a theoretical distribution, normal, geometric, binomial, whatever, you want to find quantiles of that distribution, Q distribution name. So, right, I could find out what this is by doing Q norm 1 over 11, and then the standard normal distribution has a mean of 0 and standard deviation of 1. And then we can do Q norm 2 elevenths, 3 elevenths, 4 elevenths, and so on. So I'll fill in those values, but that's where those calculations are coming from. And these are symmetric. So once I get the negative ones, get the positive ones. And then what a quantile plot does is it takes these two numbers over here meaning this one and this one. So it plots not the quantiles, but it says this is the 2 11th quantile for the data set X. This is the 2 11ths quantile for the normal distribution. Let's plot that point. So these first 2 points are over here and over here. So this point, if we zoomed in really close, is basically at is at 60 minus 1 about, right? So here's the minus 1, and here's the 60. And that corresponds to essentially where this point was. So we're plotting our coordinates like this. This goes on the horizontal axis. The x's are plotted on the vertical axis. And we oftentimes put a reference line through the middle. And the point of this line is so if our points line up closely with the line, then we would say our data is normal. The less closely it aligns with the line, the less normal we would say this distribution is. And so what you can think about is we could have like, this is what the data would look like if it was normal or something close to this. And what you can see is that at some points, probably more accurately would look something like this. Right, this distribution has a larger bar in the middle than, say, the normal distribution would have its hump in the middle. And that is being reflected by these points over here. And so one way to try and summarize what's going on in this plot if I compare kind of the slope of these points, if the line connecting those points is less steep than the line through the middle, okay, that means your data has more stuff than the normal distribution does. And when the data is very steep, like this part right here, this is corresponding to X values that were somewhere around 80 in the data set, between 80 and 90. And that's telling me that over here, sorry. So this is going from about, yeah. So this is kind of going from 80 up to 90, not above 90. So it's looking at this stuff over here. We can see that this is a little bit less than what the normal distribution should have. So when things increase more quickly than the line, like the two dots between 80 and 90, this means that our data set actually has less data over that range than the normal distribution has. So we can kind of compare the steepness of the line to the kind of steepness of the line connecting our points. And the steeper the line is for our points, that actually means the less data, we have less data in that range than the normal distribution does. And when things are flatter than the line over here, this means that we have more data over this portion of values around 70 than the normal distribution should have. So I'll stop us here. I haven't talked about how to do this in R yet, so we can pick up with how to do this, create these in R, and then more importantly, this is sure to be some questions on your next exam. Let's kind of match up, kind of identify how we could take one of these quantile-quantile plots and see what it tells us about the data. So this is kind of a more conceptual part of quantile-quantile plots. So we can talk about this after you've had a weekend to unwind. We'll pick up with quantile-quantile plots. And then we're going to start doing some statistical inference, do some permutation tests, working with chapter 3 next time. So in the meantime, I will get a homework assignment up for you guys and a reading quiz up for you that will be due Monday. The homework will be due the following Monday. Okay, well, I've got office hours tomorrow if anybody wants to come by with questions. Otherwise, have a nice weekend, everyone, and I'll see you guys on Monday.